So again, we are talking about the derivative of trigonometric functions. Let me change the title here. And I'm going to start first with visualization of the sine function. I want to convince you, or I want you today to guess, well, some of you already know, what is the derivative of the y equals sine x. Okay, so let's look at the graph of y equals sine x. Then try an educated guess of its derivative. So I'm gonna do it, let's say, from maybe I'll start with negative pi to positive pi. Okay, so this is x and this is y, and we know that the sine function, the range is -1 to 1, and let's say this is pi and this is negative pi, and in between we have pi over 2 and negative pi over 2, and we know that sine of 0 is 0, sine of pi over 2 is 1, and sine of pi is 0, and sine of negative pi over 2 is -1, so, and sine of negative pi is also 0, and the overall shape of the curve is the sinusoidal shape. And here's one cycle, not necessarily the classic one cycle from 0 to 2 pi, but negative pi to pi give us also one period that is 2 pi. And now let's try to guess what will be the shape of the derivative. And we know that the derivative is the slope of the tangent, so let's look at tangent at different places. Okay, so what struck first is that the tangent, the slope of the tangent at the summit here, or the peak, and at the bottom here will be 0. So we know that if this is the graph of y equal, let's write it here, y equals sine x, then right here at these 2 points, y prime will be 0 because the tangent is a horizontal line. Okay? Also, I'm looking at the place where I have the steepest slope. In other words, where the rate of increase of y equals sine x is the most. Well, it's right there at the 0, isn't it? And it appeared to be at 75 and 45 degrees. Indeed, it is. Maybe the graph doesn't show it, but here we're going to say that. Well, let's assume that it is, and we're going to say that y prime equals 1 here. Okay. Also, we see that we have an increase between negative pi over 2 to positive pi over 2. So we know that on this interval right there, on this interval, y prime going to be positive because the function is increasing as we move from left to right. On the other hand, and at least on this interval from negative pi to negative pi over 2, and on this interval from pi over 2 to pi, the function is decreasing, so we know that y prime is negative. Okay? Also, if we assume that the tangent here is similar to the tangent here, which is the correct assumption, and here the derivative will be 1, we have positive 45 degrees, we can say that here we have negative 45 degrees, or the derivative is negative 1. And so is the case here. Let me slide it over, and we'll have y prime equals negative 1 right there. Okay. So now I can start graphing this. I have several points, right? For instance, the derivative here is negative 1, so this is negative 1. The derivative is 0, so this is 0. The derivative here is 1, this is 1. The derivative here is 0, here's 0. The derivative here is negative 1, here's negative 1. So now I need to connect these points. Okay? We have 1, 2, 3, 4, 5. What trig function has this shape? The cosine. Precisely. So, if I'll connect and give it the a shape of a primary trig function, primary versus secondary, secondary being the reciprocal, secant, cosecant, and cotangent, well, the primary trig function that has this shape is the cosine. So, our guess that y prime equal cosine x, or we can say that d dx of sine x equal cosine x. And with this, we'll see that this is an excellent guess. And what I'll do next, I'm going to prove it. Okay? So on the next example, we'll just prove that the derivative of the sine indeed is the cosine. So again, instead of giving you the rules, I want kind of to trigger a little bit curiosity in your mind why the rules are what they are. I mean, instead of saying, okay, yeah, here's the trig function and here's the derivative, I want to encourage you to ask why. Right? So let's move on to the next page, and in this exercise, we'll ask to prove that d dx of sine x equals cosine x. So here comes the proof. Okay. Let f of x equals sine x, then f prime of x equals d dx of sine x is given by the following, is given by the limit definition of the derivative. So what is the limit definition of the derivative? F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h. One of the most important elements of differential calculus. All right? So in our case, we're going to say d dx of sine x by the limit definition is the limit as h approaches 0, and we'll have sine of x plus h minus sine of x divided by h. So far so good? Now we need to go and brush on our trigonometric identities. Do you remember the sine of a sum identity? If you have sine of a plus b, what do you have? Not quite. Sine a cosine b is 1/2 of this, and what else? Plus, well, you almost got it right. No, it's plus. It's a sine a cosine b plus cosine a sine b. Okay? If you want to keep a first and b second, Alex. question that I can answer? No? I'm sorry? I can't hear it. All right. So here's the identity: sine x cosine h plus cosine x sine h minus sine x divided by h. For reason known to me right now, unknown to you, but will become clear later on, I'm going to break it down into two parts. I'm going to write this will be the limit as h goes to 0. I'm going to group sine x. Notice that I have sine x and sine x here. So I'll factor the sine x, and I'll have cosine h minus 1 over h. And then I have what I left is the term in the middle. So I'll have plus the limit as h goes to 0 of cosine x sine h over h. Okay? So now I have two limits. I use the fact that limit of a sum is sum of the limits. And hey, yes, go ahead, Isa. How come sine x? I factor sine x and I have cosine x minus 1. Cosine h minus 1. Okay? This negative sine x is from the definition. So, notice that the variable of the limit, what is h? H approaches 0. X is x. X, as far as the limit is concerned, x is not part of the variation of the, is not a variable. So I can factor it out. So the first limit is going to read sine of x times the limit as h goes to 0 of cosine h minus 1 over h. And the other, I'll do the same thing, cosine x, the limit as h goes to 0 of sine h over h, like so. At this point, I need to tell you to take things at faith, because there are two limits here, this one and this one, that we know to be true by either graphic or by putting values in a table. We talked about what is the limit of sine of x over x when x goes to 0. And we realized by either looking at the table or the graph that it equals 1. Okay? Similar to this, we're going to say that this equals to 0 and this limit equals to 1. Proof of these two will come later. I need to take you a little bit farther down into calculus 1 to prove these two statements. Yes, Jim. How about hold on the question? Let me finish this and then I'll address your question. Okay. So, this will be shown later. Okay. These limits will be proven later. So, when we come down to it, we have sine x times 0, and then we have cosine x times 1, and that's the result, cosine x. Okay? And that completes the proof. Now go ahead and back to your question, Jim.